I have noticed that many computer science students with a limited math background struggle to process some of the important equations for physics-based animations. Here I will go through the steps to linearize backward Euler. On the right, I define some variables that we will be using throughout this video. Note that the dots over x represent derivatives. Let's start our linearization process with the velocity update formula. Our first modification requires Newton's second law. The force equals the mass times the acceleration. We simply move the mass to the left-hand side of the equation to isolate our acceleration. We then substitute it in the equation. To simplify the equation, let's move the current velocities to the left-hand side, effectively giving us the change in velocities delta x dot. At this point, we are ready to linearize our forces. To do so, we use a Taylor expansion and keep only the terms when I equals 0 and I equal 1. Adding more terms will allow for a better approximation, but likewise become higher order, which is not what we want. We modify the formula by replacing f by the linear terms of the expansion. Note that the derivative of f is a well-known matrix K, the stiffness matrix, which determines the magnitude of elastic forces. So let's replace f prime with k. We substitute the next position by its position update equation. The position terms are now cancelling each other out. We now want to remove any n+1 term from the right-hand side. We can slightly modify the definition of the change in velocities by transferring xn to the other side. With this definition, we'll substitute the next velocities. We are almost there. All we need is to regroup this delta x dot on the left-hand side. Let's transfer the mass. We then separate the terms multiplied by k. And now, we can subtract the delta x dot part of the equation. We can clean this up further by factorizing the change in velocities. See how this equation now has the ax equals b typical form. You are now free to use any linear solver to solve for the change in velocities. This should effectively give you a stable simulation. If you want more information about Taylor expansions, feel free to watch the video listed in the description.